Hi, gang. Math 5500. Starting again, my favorite part of the class, which is getting into using matrices to matrix operations for simple linear regression, setting the stage to move in and transition to multiple regression. So this is one of those videos that we're just going to build some things that are going to be sprinkled throughout. This is one of my least favorite videos, but it's just some things that we need to cover to get to the cooler stuff and other. Well, my email's just now blowing up. So anyway, what I want to cover here is linear independence, rank, and to take a look at the matrix X transpose times X, and then look at the inverse of that. So recall, I presented this in a previous email that the inverse of A, denoted A inverse, is such that A times A inverse is equal to A inverse times A, which is equal to the identity matrix. This is for square matrices. Now, we need to talk about something. I promise you I can spell. I know there's an E there, I just can't write. So independence. So we say that, how do I want to put this? I'm not going to get into this a lot because, Dr. Blau teaches our Math 5100 Advanced Linear Algebra course, but I want to get into independence and rank just enough to satisfy some things that we're going to run into with regression. So we're just going to hit the tip of the iceberg. So independence, I would say that we have a set of vectors and we'll just call this V, V1, V2 up to Vm. Well, let's not do that. Rows, we use, let's do sub k. I don't want to mess that up because we do R by M. Anyway, is linearly independent. Having a hard time writing today for some reason. If the vector equation so again, looking at this vector, so we have v1 times an x1 plus a v2 times an x2 plus a v, what I say, k times an xk is equal to 0. Has only the trivial solution. X1 equals X2 equals X sub k is equal to 0. Well, it goes without saying it, but I'm going to say it anyway. So the set of vectors is linearly dependent otherwise. All right, so let's just look at an example. Let's say that we have a matrix 1, 1, 3, 1, negative 1, 1, and 1, 2, 4. So we can create our vectors. So we can just say that vector 1 is 1, 1, 1. Vector 2 is 1, negative 1, 2. And vector 3 is equal to 3, 1, 4. All right? So we're ultimately asking ourselves, is there an x1 times vector 1 plus x2 times vector 2, and we get 1, 2, plus x3 times vector 3, which is equal to 0. So I can take this matrix. Should have made a smaller matrix. It sure would be a lot easier. See, is that right? 1, 2, 4. Yeah. And do row reduced. And I get, I did this previously. I'm not going to demonstrate this because there's all kinds of programs out there that does this for you. I'm more worried about you just getting a review of linear independence. All right. So the top row tells me that, again, let's say, x1s, x2s, and x3s. So this tells me that x1 is equal to negative 2x3, because this is saying x1 plus 2x3 equals 0, so obvious reasons. And it tells me that x2 is equal to negative x3, right? So a non-trivial solution does exist. In other words, negative 2 vector 1 minus vector 2 plus vector 3 would be equal to 0. Now, we can change this up a little bit and look at a vector, or I'm sorry, look at a matrix 1, 1, 3, 1, negative 1, 1, and negative 2, 2, 4, and repeat from above. And what we get here is we get the identity matrix. So what this tells us is it's the only trivial solution, so we have linear independence. So when, and again, these calculations are so easy, so we, I'm not going to demonstrate that here. There are online calculators that, you can do this stuff with your graphing calculator. Anyway, that's not the nature of this. Let me get another sheet of paper. The nature of this this video. All right, let's talk a little bit about rank. So the maximum number of linearly independent rows is what we call our row rank. And the maximum number of linearly independent columns is obviously called our column rank. So if A is an M by N matrix, we have upper bounds on our row rank. And our column rank. So just an FYI. All right. So the result we have is the that we saw previously is that the result of a matrix, square matrix R by R, exists only if the rank is equal to R. And an easy way to check this is to take a look at just a matrix. Let's just A, B, C, D. And we know from previous classes, hopefully, that the determinant is just taking, of course, the product minus the product. So if the determinant is equal to 0, then the A inverse does not exist. So again, just some things that you tattooed to the brain, and that will be used. It'll be sprinkled throughout the rest of the videos. I feel like there's something else I want to tell you. I'll just review very quickly. Well, if it comes to me, I'll throw it in. Let's dive into this X transpose X matrix that we see a lot. And we know that X transpose, or I hope you know by now, that X transpose looks like this. And if you don't know it yet, at least I hope it's in your notes. It's in your notes now, right? So this is going to be a 2 by n. This is obviously an n by 2. You know, again, going back to what we've talked about before, the product exists. And we're going to have a 2 by 2 matrix. And the 2 by 2 matrix, as we've seen before, looks like this. Now, the determinant here is, again, the product. Minus. Now, don't confuse these two, that the sum of the x's squared is the same thing as the sum of the x's quantity squared. They say after you've been teaching a while that you teach toward the things that people mess up. So there's a reason that I'm doing that. All right, I think I'm going to stop here and create more in the next video. So take care.